All right, ladies and gentlemen, you are at the point in your calculus career where you need to learn a bunch of different derivatives rules for all the types of functions that we're familiar with. So you may be familiar, you should be familiar rather, with this function e to the x, the exponential function. We're going to tackle that one today, and also the natural log of x, which is its inverse. Now, you may remember from pre-calc that this function, these e functions, are good for modeling exponential growth. So here in this example, I have a rumor spreading throughout the school. So you tell two friends, and those two friends tell two friends each to make four friends, and so on and so forth, right? That is exponential growth. This problem could also just as easily be about the spread of a virus, right? So super relevant to the times we live in today. Now, e is a number like pi that is so special that it gets its own name. It's equal to about 2.71, and it goes on forever just like pi. And you may recall last year that I told you that you would learn why this number was so special in calculus. Well, here is why. Today is the day. So this is the graph of e to the x. And notice it has that nice exponential curve where it increases at an increasing rate, gets steeper and steeper over time. But look at what we notice here. So at this point, 0, 1, the slope of my tangent line is 1. At this point, 3, 20.1, the slope of my tangent line is 20.1. And at -2 and 0.135, the slope is 0.135. So that's pretty interesting, right? The slope is equal to the y value of the function. This is the only function for which this is the case. And fortunately for us, it makes the derivative rule for this function really, really easy to memorize. The derivative of e to the x is itself. It is its own derivative. That's why e gets its own name like pi. Okay? Easiest derivative rule to remember in the world. So, for example, a here, the derivative is e to the x. For example, I'm not sure what happened to b, but for example, c here, my derivative is e to the 2x minus 1 times the derivative of 2x minus 1. Okay, so make your note here. This is by chain rule, so you remember for later. Okay, so the derivative rule itself, easy, but we still have to use chain rule every time we have a function within that function. And then this one, e to the 2x to the third minus 5, well, that stays the same, times the derivative of 2x to the third minus 5, which 3 times 2 is 6x squared. So easy enough rule to remember. Just make sure you're doing chain rule. At this point in your career, you're good at chain rule already, but make sure you make this note in your notes so you don't forget that's what we're doing here. Let's look at this harder example. So this asks us to find the rate at which the number of people who have heard the rumor is increasing on day 3. Okay, so that word rate should cue you in now that we're looking for the derivative, p prime of t. And I can make my life a lot easier tackling this particular example by rewriting it just like we did with our power rule. So notice I might be inclined to use quotient rule here because I'm dividing, but what's on top is just a plain old number. So I can rewrite that one as 100 times the bottom, the denominator of my function, and then to the power of -1. And that saves me from having to do quotient rule. Okay? And then to take my derivative, p prime of t, well, I now have a function within a function within a function. So my inside function is the top of the e. And then after that, I have this 1 plus e to the 3 minus t function as my second function. And then I have my to the -1 power as my third function. So that means I'm going to do chain rule twice, right? So I'm going to start with the outer function, the derivative of something to the -1 power. Well, I just multiply times -1. That gives me that 100, -100 rather. Inside stays the same. and then I subtract 1 from my power, and then times the derivative of the inside function. Well, the derivative of 1 is 0, and the derivative of e to the 3 minus t is e to the 3 minus t. And then times the derivative of my inside, which is just this exponent here. So times the derivative of that, which is clearly negative 1. Okay, and then the last thing I can do is I can combine my constants here. I get positive 100 in front for my derivative. Okay, so all of my rules still apply even though we're running into uglier and uglier functions. Alright, so now we have our rate of change of p, our derivative of p. And remember, we're looking for the rate on day 3. So that's p prime of 3, which means I just plug in that plug in 3 for every time I see t in my derivative here. And I would be reaching for my calculator if I were you, but notice I have zeros in my exponents if I simplify that a little bit. So 3 minus 3 is 0 for those. And anything to the 0 power is 1. So this becomes one I could actually do without a calculator if I were so inclined. And then 1 plus 1 is 2. And that is really 100 over 4 because of the negative exponent, which is 25. And then we should add a unit here, and our unit is, if we had people in days, or students in days, say 25 students per day. So that is it. That's the most challenging problem we're going to tackle in this particular video. I make sure you understand how I got all of my work here. Mostly it's chain rule, right? And then we're going to move on to the next page, and we're going to have one more pretty easy derivatives rule we're going to add here. So our second function that we're interested in is the natural log of x. So that's the opposite of e to the x. It's related to e to the x like plus and minus are, right? And the way we write that function is ln x is how we represent that. And its derivative is 1 over x. Okay, so easy enough. So if I asked you just for the plain old derivative of natural log of x, you would say 1 over x. We're still going to use chain rule if needed. So in this case, y prime, well, it would be 1 over 2x plus 2, because that's what's inside my natural log, and then times the derivative of that inside function, which is 2. Okay, so we can write y prime as 2 over 2x plus 2. And you could simplify that by dividing everything by 2, but it's fine to leave it alone. Here f of x is 3x, ln a natural log of 3x, and I think I asked for df dx here. It got cut off on mine. That's just the derivative of f. So same rule. We're going to do 1 over what's inside and times its derivative. And that one looks like it cancels out, right? So that's a pretty easy one to simplify, just 1 over x. Okay, and then I have a slope of a tangent line problem. So find the slope of the tangent line to g at the given x, which is x equals 1. So really we want the slope of the tangent line. We want the derivative g prime of 1. So we'll find g prime of x using my new rule. And notice we just have a plain old kind of naked natural log function here. So we'll do 1 over x. And then we have a power rule function, so these aren't going to go away. So the derivative of 3x squared is 6x, and then I want to plug in 1 here. So g prime of 1 is just going to be 1 over 1 plus 6, which is 1 plus 6 is 7. So that's the slope of my tangent line at 1. And obviously I could also figure out the tangent line by plugging 1 into this. I would use a calculator for that. And getting my point, and then writing in point slope form. So those are my 2 new derivatives rules, natural log and e to the x. and we'll come back to our trig functions in part 2 of this video.